So if we consider electrical wire and we consider a light bulb, we talked about how metal conductors obey Ohm's law. Um, and so, V equals IR, right? And so it doesn't matter how much, voltage you put in there, resistance should stay constant. So then if you double voltage, current should double and resistance will change. However, there are objects, a lot of objects that do not obey Ohm's law, where you can't just do V equals IR and assume that the resistance is going to stay the same. Resistance is actually going to increase inside a light bulb as it gets hotter and hotter and hotter. And so it acts different than a normal metal conductor. Other things that don't obey Ohm's law, diodes, and there are semiconductors that allow current to only go in one direction. Thermistors, devices that purposely change resistance based on temperature, so they're not going to obey Ohm's law either. When I mean about not obeying Ohm's law, you can still use V equals IR and you need to, but you can't just assume that resistance is going to stay the same the whole time. So if we look at this graphically, the top in part A, this is working with Ohm's law. Let's say that we had, we'll do a comparison here. Let's say this is 1 volt, 2 volts. Let's say this is 2 amps, 4 amps, right? So if we look at this spot, let's say right here, right, V equals IR, we have 1 volt and 2 amps of current. And we would find that the resistance of this object, whatever it is, would be 0.5 ohms, right? So if we look at the second step here, let's say right here, this is the same object, V equals IR. We have 2 volts, current is 4 amps, and we want to find the resistance. We divide both sides by 4. We would get 0.5 as well. So, yeah, the resistance would be the same. Right, so resistance is the same here as it is for here. This is obeying Ohm's law. Now, if you look at this graph down here, this does, it starts out linear, starts out, obeying Ohm's law, and then it kind of goes off like this, right? So if we took a look at a situation, and this is going to be hard to go exactly to scale. Try my best here. Let's say this is 1 volt, 2 volts, 3 volts. Let's say 2 amps. Let's say that's 3.7 amps. And then out here, this spot would be about let's say 4.1 amps. Okay. If we did Ohm's law for each of these spots, let's say we did it for the first one, it acts just like this. We would say, oh, the resistance is 0.5. But if we did the second spot, right, if we did the second spot, V equals IR, so we would have 2 volts, 3.7 amps. We would get a different amount of resistance, right? We would have 2 divided by 3.7 would have a higher resistance. And then even if we did this third spot, right, the 3 volts and 4.1, this would have even a much greater, and let's actually do that one. So V equals IR, the resistance here, so we have 3 volts, the current is 4.1 amps, and we want to find the resistance. So 3 divided by 4.1, about 0.73. So the resistance definitely increased. And this would be a great example of maybe like a flashlight bulb or another kind of light bulb or anything that doesn't obey Ohm's law, that as the temperature increases, thermistor, as the temperature increases, the resistance increases. When you think about electricity, it's hard not to think about Thomas Edison. And one of the first uses of electricity was heating up metals, like Edison did, to produce high thermal energy. And with high thermal energy, we can produce light. And so we've looked at that. We've looked at, the black body radiation simulation and how, if you can get an object to a certain temperature, it can produce light. And so this is him here, showing off one of his inventions. And, and this is, not that long ago. He was born in 1847, died in 1931. And it's kind of neat to think about, the contributors to science as well as technology, that not everybody, is a experimental scientist, but, they were able to use the technology to help improve our improve our lives. All right, so resistance. When we consider resistance, we have these different factors that we've talked about. It depends on the geometry of the resistor. What is its shape? How long is it? What's the cross-sectional area? And then also what substance is it? And so when we look at resistance, we have these factors. We have the resistivity. This is has to do with the type of object that we have and what kind of metal it is. The length of the resistor. The longer it is, the more resistance we have. The cross-sectional area of the resistor in meters squared. And we get a certain amount of resistance in ohms. So on your IB equation sheet, it's arranged like this. I just have it in this form here, but this may be the one that you want to write down. This is the one that you have in your equation sheet. If we want to find out how much resistance in ohms that we have, we need to know the resistivity based on the substance in ohms meters, how long it is, the cross-sectional area, and we can rearrange this equation to get this. So it's the same equation, it's just, whatever you're trying to find. What's kind of neat about this is there's a direct connection with thermal conductivity. And if you remember back from thermal energy transfer, how much thermal energy transfer there is in a period of time, it's, let's say you have two objects, right? Let's say you have, a box here, and let's say that you have another box sitting right next to it, right? So here's the other box. Try to draw this three-dimensionally here. Okay, so these two boxes are touching. So the more area that we can have, right, the more area exposed to the two, the greater the thermal energy, right? So the more area that's exposed, the smaller the thermal resistivity is, the smaller that K value, the greater the thermal energy transfer. The greater the temperature difference, right? The hotter this is and the colder this is, the more energy transfer will happen. And the smaller the length is between the objects, the quicker we'll have that there. If we think about electrical, here with a wire, we've got our wire and Q over T, which is current, right? How much coulombs per second. The greater the area of this wire, the bigger the wire is, the more current that's going to pass through. The smaller the resistivity constant is, copper versus aluminum. Copper is going to have a smaller number here. It's going to have more current. That wire is going to have more current passing. The greater the voltage, right? The higher the voltage is, the more current will pass through, and the shorter the length there is, the more that the current will pass through. So it's kind of neat to see the parallel between these two because, we have a lot of these similar factors. Area, the areas are the same in comparison here. The greater the area, the higher the temperature difference, the greater the voltage difference, the more current you'll have, the shorter the lengths, the greater you'll have, and then the resistivity and the thermal resistivity, the greater you have. And then same with time, right? The more charge, the more coulombs per second, the greater the current. And again here, the more joules per second, the more that you'll have. All right, so in this one, we want to find the resistivity of substance that has a resistance of 1,000 ohms, and the length of the material is 4 centimeters. Its cross-sectional area is 0.2 centimeters squared. So I'm going to have you try this. Be careful with your units there, and go ahead and solve that, and when ready to check, you can hit play to continue. All right, so we have our length. With centimeters cubed, we're going to have to cube our conversion. So it's 100 centimeters cubed equals 1 squared meters cubed, not cubed, squared rather. So 100 squared centimeters squared is equal to 1 squared meter squared. So that's our cross-sectional area, and we've got that. We've got our length, and we can find our resistivity value. And for this substance, it's 0.5 ohm meters. So that's rho, that's the resistivity constant for this substance.